In the world of nuclear physics, some atoms are inherently unstable. To reach a lower energy state, they spontaneously emit particles and energy. This process, known as radioactive decay, is entirely random for a single atom but follows a predictable pattern for large groups. While we cannot predict exactly when one specific atom will decay, we can calculate the statistical probability for a billion atoms. The more unstable atoms we have, the more decays we observe per second, creating a predictable mathematical relationship. The most important concept in radioactive decay is the half-life. It is the fixed duration of time required for exactly 50% of a radioactive sample's nuclei to undergo decay and transform into a different, more stable element. We model this behavior using an exponential function. The amount remaining, n of t, equals the initial amount multiplied by 1/2 raised to the power of time divided by the half-life duration. This allows us to predict the sample size at any point. Visually, this relationship is an exponential decay curve. Notice how the graph never actually reaches zero, it asymptotically approaches the x-axis. As time progresses, the rate of decay slows down because there are fewer unstable atoms left to decay. It is a common mistake to think decay is linear. In linear decay, a constant amount is lost per second. In exponential decay, a constant percentage is lost. This distinction is vital for accurate calculations in medicine, archaeology, and power generation. We often use the decay constant, lambda, to describe how quickly a substance disappears. It is inversely proportional to the half-life. A very short half-life means a very high decay constant, indicating a highly unstable and active radioactive substance. Let's look at iodine-131, used in medical treatments. It has a half-life of 8 days. If we start with 80 grams, after one half-life, 8 days, only 40 grams remain. After another 8 days, we are left with only 20 grams. To find the amount after 24 days, we plug the values into our equation. Since 24 divided by 8 is exactly 3 half-lives, we calculate 1/2 to the third power, which is 1/8. 80 grams divided by 8 leaves us with exactly 10 grams. Carbon-14 dating uses these principles to age organic matter. If an ancient wooden tool contains only 25% of the carbon-14 found in living trees, we know 2 half-lives have passed. Multiplying 5,730 years by 2 gives us an age of 11,460 years. A helpful shortcut is to remember the fractions. After n half-lives, the fraction remaining is always 1 divided by 2 to the power of ln. This mental math helps quickly estimate the remaining activity of a source without a calculator. Different isotopes decay at vastly different rates. On a graph, a substance with a short half-life will show a very steep drop-off, while a substance with a long half-life, like uranium-238, will appear almost as a flat line over human timescales. The rate of decay is called activity, measured in becquerels. Activity is directly proportional to the number of atoms present. As the number of atoms decreases over time, the radiation emitted by the sample also decreases following the same exponential curve. Scientists often use logarithms to analyze decay. By taking the natural log of the amount remaining and plotting it against time, the exponential curve turns into a straight line. The slope of this line is the negative decay constant, making data analysis much simpler. Let's summarize. Radioactive decay is a random process that follows a predictable exponential pattern. The half-life is the constant time it takes for half a sample to decay, and we use the exponential function to calculate the remaining mass or activity over time. Test your knowledge. If a 100-gram sample has a half-life of 10 years, how much will remain after 30 years? Think about how many half-lives occur in that time and apply the halving principle 3 times. The answer is 12.5 grams. 30 years represents 3 half-lives. We take 100, halve it to 50, then to 25, and finally to 12.5. Thank you for joining this lesson on nuclear physics. Generated by Vision Solve AI.